Our next topic is something called the central limit theorem. Now I'm just going to sort of write this up here and sort of discuss our way through it. And it might seem at this time like it doesn't really relate to what we've been doing so far, but hopefully once we get this discussed through, and I'll show you some examples, I hope it will become clear. So the central limit theorem says this. It says if a sufficiently large sample is taken from a population with mean equal to mu and standard deviation equal to sigma. And so if we take a sufficiently large sample, now sufficiently large is a notion we're going to talk about later. Let's just assume for now that we have taken a sufficiently large sample, whatever that means, and we've taken that from a population. Let's assume the population has a population mean of mu and a standard deviation of sigma. So let's assume for now that mu and sigma are known. If the sample is sufficiently large, then there are three results that are true. The number one is that the sample means, let me say that a little bit differently. The population of sample means is approximately normally distributed. That says the population of sample means is approximately normally distributed. The sample means are centered at mu, the population mean, and the third the sample means have standard deviation equal to sigma. Now that's a lot of words, and it might seem sort of cryptic and not particularly relevant now, but we'll come through this a few times and you'll see where we're going with this. But for now, this is the statement of the central limit theorem. It's the central limit theorem. This is a proven theorem, just like the Pythagorean theorem or any other theorem you've ever heard of. This is a proven mathematical theorem. It says if a sufficiently large sample is taken from a population. So we have a population of, it doesn't matter what it is. The population could be the population of tree heights. It could be a population of the weights of a certain organism you're measuring. Maybe you're working with wildlife husbandry and you're working with coyotes. So we have the weights of coyotes. It can be any population. It can be the time required for medication to reach a certain concentration in the bloodstream. It doesn't matter what the population that you're dealing with. If the population has population mean mu and standard deviation equal to sigma, if you take a large enough sample from that population, then there are three things that are true. The population of sample means is approximately normally distributed. The sample means are centered at mu, and the sample means have standard deviation equal to sigma. Now I'm going to erase some of this so I can sort of draw some pictures here. Now here's what that means. If we have a large population, let's suppose we have the population of all patients that receive a certain medication. That might be a huge number. But we take a sample, and for now, let's assume that 40 has met this sufficiently large requirement. We'll talk about sufficiently large in just a little bit. But for now, let's just assume that 40 is a sufficiently large sample, and so we've taken a sample of size 40. Well, if researcher number 1 takes a random sample of 40 from this huge population, researcher number 1 will compute from that sample, they will compute X bar number 1. So researcher number 1 would compute X bar number 1. But researcher number 2 is doing a similar work. And so researcher number 2 also goes to that population, takes a sample of size 40. Almost certainly there will be a different group of items in that population, or excuse me, in that sample. And so researcher number 2 might compute sample mean number 2, and it is almost certain that those are not going to be equal to each other because the two researchers will have a different sample that's taken from that huge population. If researcher number 3 and 4 and 5 and 6, if we have several researchers all doing work with this population, and they take a sample of size 40 from this huge population, each of them will have a different sample. They might conceivably share 1 or 2 people in common, but the overwhelming majority of the samples will be different data values. And so when researcher number 1 adds up their data and divides by 40, researcher number 2 adds up their data values divided by 40. When all these different researchers compute all these different sample means, researcher 3, researcher 4, and so on, we will have a collection of sample means. Now, theoretically, we could take every conceivable sample of size 40. Now pause and think about that for a moment. We could theoretically take every conceivable sample of size 40. Now, let's simplify it. Suppose the population has 3 data values, and suppose our sample is size 2. Well, there's one possible sample, AB. Here's another possible sample, AC. And here's the other possible sample, BC. If we only have 3 data values in our population, and we only take samples of size 2, these are the only 3 possible samples that could be generated. But if we have a population that is huge, numbering in the tens of thousands, potentially in the millions, and we randomly select 40 data values, there would be an astronomically huge potential number of possible sample sizes that could be generated. Theoretically, that could be done. We could find all of them. Whenever we say we have all of something, that means we have the population of them. The population of wildebeest in Africa means all of the possible wildebeest. The population of patients receiving a medication means all the patients that have received that medication. So the phrase population of refers to all the possible values of that type. And so if we have all the possible samples of size 40, we have the population of samples. And if we compute the sample mean for each of those, then what we have is the population of sample means. What we have is the population of sample means. So anytime you do this experiment, you take 40 people from that population, you compute the sample mean, you have selected one of these potential sample means out of this population of sample means. And what the central limit theorem says is this: if we have all of these sample means, then statement number 1 says we get to use the normal curve. And so we have, and we will have, and we will use this very often, a new picture to work with. This part's the same. It's the sample the normal curve. This part is the same. It's the standard scale. But this scale is now different. We will no longer use x to represent that in this scenario, because these are not raw data values. These are now the sample means. Every possible sample mean falls on this axis somewhere. And what the central limit theorem says is we get to use the normal curve to analyze sample means, just like we got to use the normal curve to analyze the raw data for a normal population. But it says this: anytime you have a normal distribution, you must know two things. You must know where is it centered. Well, that's what this next line says. The sample means are centered at the original population mean mu. So these are centered at the original, for our purposes, given population mean mu. And anytime you're going to be dealing with a normal curve, you need to use the standardizing formula. We need to know z is equal to, now before we used x minus mu over sigma. Now why did we use that? This corresponds to the type of data we're working with. In our case, we're not working with raw data values, we're working with x bars. So our new formula is going to be z is equal to not x minus mu, it's x bar minus mu. X bar because this is a mean of a sample taken from the population. So we have x bar because this is the x bar scale. Mu is the same. And now the last piece is the sample means. These also have a standard deviation. But the raw data values correspond to the standard deviation. The x bars don't correspond to the standard deviation. And here's the new piece. The x bars, the standard deviation of the x bars is not sigma. It is sigma over, I'm going to write this differently. The x bars don't give rise to sigma. The x bars give rise to sigma over square root of n. So that might seem to be a little blurry, a little complex, but we'll be able to simplify this out a little bit. So let's kind of put this all together here. All right. If n is sufficiently large, and again, we'll talk about sufficiently large later. If n is sufficiently large, then, number one, we get to use the normal curve. This is the z scale. This is the x bar scale. And the z formula to translate from the x bar scale to the z scale is given by x bar minus mu over sigma divided by square root of n. This is the z formula we use to translate from the x bar scale to the z scale. This is the formula we use to translate from the x bar scale to the z scale. For now, just be able to know that if we have a sufficiently large sample, we get, number one, we get to use the normal curve. This bottom scale is not x's, it's x bar. And this is the formula to translate from one scale to the next. It's x bar minus mu over the original sigma divided by the square root of n. Now we'll do several examples of that, enough that you'll get used to it. But that's the formula we're going to use. Anytime we take a sample from a population, this is the procedure. Notice that n is in the formula. And we'll do several examples of this in the next video.